Let's solve dynamics of mathematical pendulum. Mathematical pendulum is a mass m on massless string of length L. There is a rotational joint. So we can give some input quantities. So m is a mass of particle, L is a length of string. We measure rotational angular displacement as an angle phi, and we can say that there were some, at the beginning of the process, at the beginning of the motion, there were some initial conditions. First initial condition is for initial angle. So initial angle is an angle in time 0. So it was, let's say, phi 0. Let's say this is phi 0. And second initial condition is for velocity, where velocity, angular velocity, is a time derivative of phi. At time equals 0, let's say it was 0. So it is second initial condition. And the task is to find motion of pendulum in time. So how it moves, how angle phi changes during the time. Okay, so first we need to draw free body diagram. So usually, not usually, but always, we must draw free body diagram at general position, not at special position. So this is good general position. So I draw M in this direction. This angle is phi, and we must draw forces acting on this particle. So vertically there acts gravity force. In this string we have reactional force, so this is a force in the string S. Regarding the coordinate system, it's good to solve this motion in T and B coordinate system. So we use T and B coordinate system. So there is T, and perpendicularly to this there is normal line. So I can draw unit vectors, base vectors t0 and n0 like this. Something is missing here, because these two forces can't be in equilibrium. And what is missing is inertial force. Inertia, D'Alembert force, has two components, tangent and normal. And because this is a positive direction of t-axis, we draw dt in opposite direction. And because this is positive direction of normal, so we draw against this direction force dN. Okay, so free body diagram is done, and generally we can say that sum of all forces plus D is equal to 0. And which forces are there? There is force S, there is force G, and that's all, plus D is equal to 0. This is a vector equation of dynamic equilibrium. So this is vector equation of dynamic equilibrium. So now we can write component equations, because this is two-dimensional case, so we have two component equations in t and n directions. First equation in direction of tangent is dt plus, and there would be component, there is an angle phi of g-force projected when we project g-force to tangent. There is a perpendicular line, so we get g by sinus phi. Yeah, and that's all. In normal direction we have dn plus cosine component. Okay, so normal component of g, so it is g cosine phi and minus force S. This is force in the string. So these two equations so let's write for specification. G is m by g. Tangent component of D'Alembert force is m by at, and normal component of D'Alembert force is m by an. It's a normal acceleration. Normal acceleration we can draw in this direction, and tangent acceleration we can draw in this positive direction. Calculation of tangent acceleration of rotational motion, I think you know, it's L, its diameter, by angular acceleration, phi with two dots. And normal acceleration of rotational motion is L, its diameter, by square of angular velocity, where angular velocity is first derivative of phi with respect to time, and angular acceleration is second derivative of phi with respect to time. Now we can substitute into first and second equation. So first equation we can write dt is m by at, where at is L by phi with two dots, plus g is mg by sinus phi is equal to 0, and second equation m dn is m by an, so it's L phi dot square plus mg cosine phi minus s is equal to 0. In first equation we can cancel mass, not in second equation, because there is this force and this term doesn't contain mass. So for further calculation we will use this equation because it's convenient. So we can rewrite this equation into this form. And this is very important equation. So this is principal equation of motion. Because this is system with 1 degree of freedom, so we get the same number of principal equations. So in this case only one principal equation. And why it is principal? Because there are no reactions. There are only inputs, input forces. Let's say some representative of input force is g, gravity, acceleration, and there are only output parameters, output quantities, so kinematic quantities of the motion. So because it is, so this is a reason why we call it principal equation. No reactions. So now we would like to solve this equation to get phi in time. This is a differential equation of second order because there is second derivative with respect to time and it's homogeneous because right side is equal 0. And unfortunately it is non-linear because there is term sinus phi. Sinus curve is not linear. So in fact in second class of university we can't solve non-linear equations. So we can make some process to make this equation linear. Linearization. So we can simplify the process a bit. If we can say that sinus phi can be very similar or almost equal to value of phi when we count phi in radians. Why it is possible? When we draw graph, there is x and y, there is 0. And we draw this line is y is equal x, so there is 45 degrees. If there is 1, there is 1 too. If we draw a sinus curve, so it means y is equal sinus x, so this is a solid line and this will be dashed line. Okay, there is amplitude 1 because there is 1. So this curve starts from the angle 45 degrees too. So in very small area from 0 we can consider that function y is equal x is approximately equal to function y is equal sinus x. So there is a very small difference between values. So we can use this and this is process of linearization, because this is linear function and this is nonlinear function. And for your attention, it is also applicable for tangent. Okay, it's the direction of tangent around 0 is also 45 degrees. So tangent phi is approximately equal to phi 2. And what is it? Small area. So when phi is less than 5 degrees. Okay, so if we consider that we keep angle less than 5 degrees, so there will be only a small motion, we can say that phi is approximately, or sinus phi is approximately equal to phi when we measure this phi in radians. So we can rewrite this equation into this form. Phi with two dots is equal, plus g over L phi is equal to 0, and this is linear equation, linear differential equation. We can solve it. So, solution. We can write a characteristic function. Characteristic function. We substitute phi by lambda, and how many dots? So it's equal to power of lambda. So lambda powered by 2, because there are two dots, plus g over L, and there is no dot, and so there is 0 dots, so there is lambda powered by 0, and everything powered by 0 is 1, is equal to 0. So we can calculate lambda. It is, or let's say lambda square, g over L, then lambda is square root of minus g over L. But we can't deal with negative values under square roots, so we must use complex values. So I can write it like this. So it is minus square root of I g over L, and it is lambda 1, lambda 2, because we can write plus minus here, okay, because we apply square root. So let's say lambda 1 is I g over L, and lambda 2 is minus I g over L. After that, we can write fundamental system. Fundamental system. This is fundamental. So fundamental system is E powered by lambda 1 t and E powered by lambda 2 by t. So solution we can write in this form. Phi in t is equal constant 1 by E powered by lambda 1. Lambda 1 is this. So it is g over L by t plus C2 E powered by minus Ig over L square root by t. So this is solution, but we don't know C1 and C2. We are going to calculate it from initial conditions. for this, because we have first initial condition for phi. So first initial condition that phi in time equals 0 is 0, and second initial condition phi with dot in time equal to 0 is 0. Sorry, I made a mistake here. It's not 0, it's phi 0. Okay, so for application of these initial conditions, we need second derivative of our solution. So if I make a second derivative of our solution, it is this. This is our solution. And we make second derivative. Sorry, first derivative. So we need to find phi with dot is d phi over dt. So we use this equation for making a derivative. So it is c1 by I g over L e I g over L, there is minus, so it is minus c2 I g over L e I g over L t. Okay, so this is second equation and first derivative of this function. And now we will apply these initial conditions. So first initial conditions we substitute into this equation. So phi 0, because when time is 0 we have solution phi 0, is equal c1, and there is e powered by something by t, and when t is 0, because it is initial condition, everything by 0 is 0, so this is e powered by 0, everything powered by 0 is 1. So I can write 1 here, but I don't do it. Plus, and again there is c2 by 1, because t is 0 in power in the exponent of e. So this is very simple application of first initial condition. And second initial condition is for velocity. Velocity at beginning was 0, so I write 0 here, and I substitute time for time equals 0. So I write t1 by I g over L by e powered by 0, because time is 0, so it is 1, minus c2 by I g over L by 1 again. And because this is the same, we can cancel it against 0 left side of equation. So finally we get two very simple equations. c1 plus c2 is phi 0, and 0 is c1 minus c2. From second equation follows that c1 is equal to c2, and from this follows that c1 equals c2 is equal to phi 0 half. So we can rewrite this solution. Phi in time is equal to phi 0 over 2 by e I g over L powered by time plus phi 0 over 2 e I g over L square root powered by time. So this is solution and it is done. But this is not so nice. Who can imagine this function? I don't expect many of us can imagine this. So we will continue in simplification. I think you know that if we have a complex number, so E Euler number powered by E alpha can be written as cosine alpha plus E sine alpha. Okay, and we can substitute here. So first we take this term, so E powered by Eg over L square root time can be, following this rule, can be rewritten as a cosine of g over L square root by time plus I sinus the same argument. And in case of this term, it is minus I g over L so we have two roots, lambda 1, lambda 2. It is plus minus square root of minus g over L, but we can handle negative numbers under square root, so we use complex numbers. So we can put out the brackets I, it's a complex unit, it's a plus minus I, and there is g over L only. So first root is I by this square root, and second root is minus I by this square root. Then we write so-called fundamental system. It is E powered by lambda 1t and E powered by lambda 2t. And final solution is this. Phi t is C1, it is constant, by this term, it's from here, because E powered by lambda 1 is this, so it's square root g over L by t plus C2, what is a constant, E powered by minus square root g over L by t. These constants are still unknown and we can calculate them from initial conditions. You will see soon that for application of initial conditions we need first derivative of this function. So phi with dot, it's a first derivative of phi with respect to time. What is C1? It is constant by, this is I square root of g over L E g over L by t minus C2 I g over L square root by E g over L time. So we have two initial conditions. First initial condition is for angle at time equals 0 and it is phi 0. And second initial condition is for velocity, angular velocity. When time is 0, the velocity was 0. And we use these conditions and apply it for these two equations. So when we substitute first initial condition to this equation, we get phi 0 is equal C1 by E powered by something by t when time is 0, everything by 0 is 0 too, and everything powered by 0 is 1, even if it is e. So e powered by 0 is 1, so I don't write 1 here. Plus c2 by the same, it is also 1. Second initial condition is for this equation. So phi at time 0 was 0, and there is C1 Ig over L by 1 minus C2 by Ig over L by 1 again. And because these values are same, we can cancel them against right side where is 0. So finally we get these equations, very simple equations. So there is phi 0, it's C1 plus C2, and second equation 0 is C1 minus C2. From this follow that C1 is equal to C2, and from this follow that it is equal to phi 0 half. Okay, so now we can write solution. So solution is phi in time is equal phi 0 over 2 by E G over L by time plus phi 0 over 2 E G over L by time. This is final solution. This is course of angle in time. But this is quite complicated function, and I guess very few people can imagine what is the graph of this function. So we will simplify it. Simplification. I'm sure you know that if we have Euler's number powered by complex unit by angle, we can write it in this form. It is cosine of alpha plus I sinus alpha. Okay, so let's apply it. We have this term. Okay, so let's rewrite it in accordance this rule. So it is cosine of G over L by T plus I sinus G over L by T. And when we rewrite this term, it is G over L by time. So it is cosine G over L by time, but there is a number minus here, plus I sinus minus G over L by time. Okay. So another rule, because cosine is even function, so we can say that cosine of minus alpha is equal cosine of alpha. So these two terms are the same. And if we have odd function, so sinus of minus alpha is minus sinus alpha. So I can rewrite this solution that phi t is equal to phi 0 over 2 by cosine g over lt plus e sine g over lt plus phi 0 over 2 by cosine g over lt minus I sine g over lt. And if we put out the brackets phi 0 half, we get that there is 2 cosines of g over lt, and this is cancelled because it's the same one time it is plus and second time it is minus, so it is phi 0 cosine g over lt. So this is final solution in very simple form. And if we want to draw a graph, phi in time, so it will oscillate in limits phi 0 minus phi 0 because there is a pendulum, there is balance position, there is phi 0, so it oscillates phi 0 to in these limits. Okay, with some period, so I can draw this. Yeah. There is time 0, there is 1 period, 2 periods, 3 periods, 4 periods, and we start from phi 0 here. And we go down, there are half of interval, so we go down, this is cosine curve, and we are back, and we are down, back. So this is cosine function, a cosine function. And I think now you can imagine the solution very well. The last question is, what is the period of this motion? The answer is very simple. When we go back few steps, so we have solution phi with 2 dots plus g over L, phi is equal to 0. This is a principal equation of motion. So it's possible to prove that this value is omega square. What is omega? Omega is a natural frequency of the system. So omega is square root of g over L. Notice that this is an argument of solution. And this omega is in radians per second. So if we use that omega is 2pf, where f is frequency in hertz, So we can say that natural frequency, so this is in fact angular natural frequency, and this is natural frequency, so it is 1 over 2p by g over L, and it is in 1 over second what is hertz. And we know that frequency is inverse value to period. So period t is equal 1 over f, and it is 2p over g over L by square root, and it is in seconds. So this is period.